All right, in chapter 3, section 6, we'll be looking at stoichiometry. And when people talk about the hard part of chemistry, a lot of them are talking about stoichiometry. And I will say that it's not that hard. It just takes a little bit of being systematic as you're going through and doing the problems. So first thing we want to do is we want to look at a balanced chemical equation. And I've selected a very simple one. Hydrogen plus oxygen gives us H2O. All right. Well, when you look at this problem, how you may have thought about this up to this point is, well, if I take 2 molecules of hydrogen and 1 molecule of oxygen, it will produce 2 molecules of water. And while that is a valid way to think about this problem, it's not particularly useful. Well, first of all, we never just take 2 molecules of hydrogen and 1 molecule of oxygen and produce 2 molecules of water, because we don't run reactions at that scale. We run reactions where we have lots and lots of molecules. And we have a term that we use for lots and lots of molecules, and that term is moles. So the way that I want you to think about this reaction when you see an equation written like this is not to think in terms of molecules, but to think in terms of moles. So you can think of this as 2 moles of hydrogen plus 1 mole of oxygen gives us 2 moles of water. Now, we don't necessarily have to do 2 whole moles of hydrogen and 1 whole mole of oxygen. We could do less than that. We could do more than that. But think about it in terms of moles. If we were to have 2 moles of hydrogen and 1 mole of oxygen, what would the mass of that be? Well, since hydrogen has an atomic mass of 1.01 and H2 would have a molar mass of 2.02, and we have 2 moles of it, would be 2 times 2.02, so 4.04. For oxygen, well, oxygen has an atomic mass of 16. 16 times 2 gives us 32, so 32.00 grams of oxygen. For water, 2 moles of H2O, H2O is 18.02 grams, so grams per mole, so that would be 2 times that number at 36.04. So that's one way that we could think about this. Now, doing calculations to convert between, if I know how many grams of hydrogen I have, how many moles or how many grams of oxygen am I going to need? Well, there's not a direct calculation for that. So that means that we can use something that we call the roadmap. And so, or something I call the roadmap. Other people will call it different things, but I call it the roadmap. And it's just a way of solving problems that uses a conversion factor in between each box. So we can calculate the mass, how much mass of one thing is needed in order for another thing to be true. So you'll notice here that we've got mass of A and to moles of A, and to convert between that, we use the molar mass. So mass to moles, molar mass. Also, when we go from moles to mass, we also use the molar mass. So often when I'm in class, I'll get my students to kind of chant it out loud when I say mass to moles, and they'll say molar mass. It's kind of exciting, I guess. All right. And then moles to moles, we'll use the mole ratio in the equation, and I'll show you how that works here in a moment. And then here, moles to mass, we'll use the molar mass of B. So let's consider this particular reaction where we've got the combustion of glucose. So we've got C6H12O6, and we burn it in oxygen. And since this is a combustion problem, we will convert it into carbon dioxide and water. Well, the roadmap can help us answer questions like this. How many grams of oxygen are required to burn 2.00 grams of glucose? So if we know how many grams of this we have, we can figure out how many grams of the oxygen we're going to need. Likewise, if we burn the 2.00 grams of glucose, how many grams of carbon dioxide are going to be produced? In a similar fashion, how many grams of water are going to be produced when we burn this many grams of glucose. So this is a pretty straightforward kind of calculation, and if you just follow the steps, you should be able to do this pretty easily. All right, so let's look at the first one. How many grams of oxygen are required? Okay, well, there's not a direct calculation, as I said, but if you follow the steps here, every time you move from one box to another, you multiply it by a conversion factor or divide by a conversion factor, then you can get to the next box. So for the 2.00 grams of glucose, we want to convert from the mass of glucose to the moles of glucose. We'll need to use the molar mass of glucose. The molar mass of glucose, as we did on a recent problem on the in-class assignment, is 180.18. All right, and we'll have to divide. That will get us to the moles. And then you'll notice that we can cancel out, do some dimensional analysis here, and cancel out the grams of glucose. Next, if we want to go from moles to moles, well, moles to moles, we use the mole ratio. I usually, when I'm doing this in class, I say moles to moles, and I get my students to say ratio. So moles to moles ratio. And the ratio is the ratio of these coefficients in the balanced equation. Since we're trying to get to oxygen and we have glucose, it's going to be a 6-to-1 ratio. So 6 moles of oxygen are required for every 1 mole of glucose that is consumed. All right, so, and then moles of glucose is going to be canceled out. And then finally, we want to convert from the moles of oxygen to the mass of oxygen. Well, moles to mass, we use the molar mass. The molar mass of O2 is 32.00 grams per mole. And so our moles of oxygen will cancel out. And then we can just put the number in. 2.13 grams of oxygen will be consumed. All right, so that's how many grams of oxygen are required. Now, here we're figuring out how much of a reactant is required, but we can also figure out how much product is going to be produced. So, again, we'll have to use the roadmap, but we're going to go to a product instead of the reactant. And so here we'll start with our 2.00 grams of glucose. Mass to moles, we'll use the molar mass of glucose again. So, and then you'll see the grams of glucose cancels out, and we're left with moles of glucose. Next, moles to moles ratio. The ratio here is the ratio of these coefficients in the balanced equation. So 6 moles of carbon dioxide for every 1 mole of glucose. Now, I'm going to warn you, it's not going to always be 6. We'll have other reactions where we have different coefficients. All right, so we have a 6-to-1 ratio here. Moles of glucose cancels out. Next, we want to convert from the moles of oxygen, or moles of carbon dioxide, to the mass of carbon dioxide. That means we need the molar mass. So moles to mass, molar mass. Our molar mass of carbon dioxide, this is one we did earlier in this presentation, and that comes out to 44.01 grams of carbon dioxide per mole of carbon dioxide. And our moles of carbon dioxide cancels out. Okay, so now that we've done that, we just do the math. We punch that into our calculator, and we get 2.93 grams of carbon dioxide will be produced. Next, we want to look at water. Calculating for water is very similar to what we did with carbon dioxide. The only thing that will be different is we're going to have a different molar mass, and it'll look a little bit different when we do this. So our first step is exactly the same. Mass to moles, molar mass of glucose, 180.18. We'll cancel out those grams. Moles to moles, our ratio here is still 6-to-1, and as I mentioned, it's not always going to be 6-to-1. It just so happens in this one, we have 3 coefficients that are 6. So 6 moles of glucose for every 1 mole, 6 moles of water for every 1 mole of glucose. Then we'll convert from moles to mass, and we'll use the molar mass. Molar mass of water is 18.02. So 18.02, and our moles of water cancels out, and we can put 1.20 grams of water. Okay, well, let's wrap up this problem by looking at a summary of this problem. So here is our summary of the glucose problem. When we burned 2.00 grams of glucose, we calculated that it would require 2.13 grams of oxygen, so that much would be consumed. We would produce 2.93 grams of carbon dioxide and 1.20 grams of water. So that is our summary. One last thing that I want to point out before we're done with this problem, and that is that the law of conservation of mass can be demonstrated by looking at these calculations. So if we look at the total mass of the reactants, we have 2.00 plus 2.13, and that gives us 4.13 grams of these reactants. For our products, we have 2.93 plus 1.20, and again, that gives us 4.13 grams. Okay, so now we're going to look at 59 and 60 on the in-class assignment. Number 60, which we're going to do first, number 60, is a little bit different than what we just did. But I had to fit it in here somewhere, and this seemed like a good place to fit it in. All right, so let's look at this real quick. So Epsom salts, a strong laxative used in veterinary medicine, that's extra information. You don't need to use that in your calculation, is a hydrate, which means that there are a certain number of water molecules included in the solid structure. The formula for Epsom salts can be written as MgSO4.x H2O, and the X is some whole number. It's an integer. All right, so and it is an integer. So what we want to do is we want to figure out what X is, right? That's the goal. And so here it says that when 5.061 grams of this hydrate is heated to 250 degrees Celsius, all of the water of hydration is lost, leaving 2.472 grams of magnesium sulfate. Okay, so there's two things that we want to use here. First, we want to figure out how much water was removed. So we'll do 5.061 grams, and we'll subtract the 2.472 grams, and that's going to give us the mass of the water. All right. So all right, and that gives us 2.589. So 2.589 grams of water was baked off. All right, so this is our hydrate, and this is our anhydrous salt. All right, so now we'll need to do a couple of calculations here. One of our calculations is going to be how many moles of water is that? So we'll do 2.589 grams of H2O, and we'll divide by the molar mass of H2O, and the molar mass of H2O is 18.02. All right, and if you're wondering, how do I come up with that number? It's pretty easy. That is the number that we get from the periodic table, our periodic table when we add 1 oxygen and 2 hydrogens. So if I do 16.00 plus 1.01 plus 1.01, and that will give us 18.02. So 2.589 divided by 18.02. And the number that we get, we have 4 sig figs, so I'm going to write this as 0.1437 moles of H2O. All right, now that we've done that, let's take the 2.472 grams of MgSO4, and this is not the hydrate, we'll need to get the molar mass of magnesium sulfate. And so for the molar mass of magnesium sulfate, we've got magnesium, which is 24.31. So 24.31 plus a sulfur, 32.07. So 32.07 plus we've got 4 oxygen. So we'll do 4 times 16.00. So plus 4 times 16.00. Don't have to put the 0.00 in there, but all right, and we get 120.38. So 120.38 grams of MgSO4 per mole of MgSO4. Okay, and so now we will divide. So 2.472 divided by 120.38, and that gives us 0.02053. So 2053 moles. All right, and so now our last little bit of this calculation, and I kind of ran out of room here, so I'm going to go up to the top. So X is going to be our moles of water, which is the 0.1437, so 0.1437 moles of H2O. And we're going to divide that by the moles of magnesium sulfate, which is 0.02053 moles of MgSO4. And hopefully we're going to get a whole number there. So 0.1437 divided by 0.02053, and we got 6.9995, which I think we can round that to 7. So that comes out to 7. That means that our formula for the hydrate is MgSO4 dot 7 H2O. And that is how we determine what the formula for a hydrate is. All right. So I know that that particular problem didn't fit in perfectly. That did not fit in perfectly with talking about stoichiometry, but I wanted to get that problem in, so that's why I put it there. All right. So let's do number 59. 59, we have several brands of antacids use aluminum hydroxide to react with the stomach acid, and the stomach acid primarily contains hydrochloric acid, HCl. And so we want to first balance this equation, and you'll notice I've left some spots here for balancing the equation. So for the, if we look, we've got hydrogen in not hydrogen in everything. We've got oxygen in 2 things here, so we could start with oxygen. We've got hydrogen in 3 things, so we want to save that for last. We've got aluminum in 1 thing on each side, so that's good. And we've got chlorine in 1 thing on each side. If we look at the periodic table, because you remember I like to go with the biggest one first. Well, chlorine is our biggest element, and it's in 1 thing on each side, so we're going to balance that first. We've got 3 chlorines here and 1 chlorine there. So I'm going to put a 1 here to lock those 3 chlorines in place, and then put a 3 out front for HCl. So now chlorine is locked in place. Let's do aluminum next. Aluminum is, we've got 1 there, so we'll put a 1 over here. And then finally, let's look at oxygen. So for oxygen here, we've got 1 times 3 times 1. That's 3 oxygens that are locked in place. And then over here, we'll need to put a 3 in front of the H2O. And then finally, if we do look at hydrogen, because that's the only one we haven't checked, 1 times 3 times 1, that's 3 there, 3 here, 3 plus 3 is 6, and then 3 times 2 is also 6. So we've got a balanced equation. We're good there. The next thing that we want to do is we want to calculate the number of grams of HCl that can react with 0.500 grams of aluminum hydroxide. Now, the way that I like to set this up is to write out the roadmap for each problem that we're going to do. So the roadmap for this is going to be, what do we know? We know our mass of aluminum hydroxide. All right, so that's the quantity that we know. And we're trying to get to the mass of HCl. So we're going to go from mass of aluminum hydroxide to the moles of aluminum hydroxide. All right, to the moles of HCl, to the mass of HCl. All right, we're going to need to get the molar mass of aluminum hydroxide and the molar mass of HCl. That's easy enough. We can find that on our periodic table. So I'll come over here. Let's calculate those real quick. Aluminum 26.98. So let me clear all that. 26.98 plus 3 times 16. So 3 times 16 plus 3 times 1.01. So 3 times 1.01. And that gives us 78.01. So that will give us our molar mass for aluminum hydroxide. Since that's the first number that we need here, so 0.500 grams of AlOH3, and our molar mass is 78.01 grams of AlOH3 per mole of AlOH3. Next, we want to go from moles of aluminum hydroxide to moles of HCl. Again, we're going to use the coefficients in the balanced chemical equation, so we'll do 3 moles of HCl for every 1 mole of aluminum hydroxide. So 3 moles HCl for every 1 mole of aluminum hydroxide. If you ever get to a point and you're not sure which thing is going to go up on top and which thing is going to go in the denominator, then that's when you want to do your dimensional analysis to make sure that you're getting the right units. All right, next we're going to want to get our molar mass, because for moles to mass, we use the molar mass. Our molar mass for HCl is 35.45 plus 1.01. So 35.45 plus 1.01. And that gives us 36.46. So 36.46. All right. And I made a mistake. I like to make at least one mistake every day. It helps people realize that I'm human. All right. So 36.46 grams of HCl per mole of HCl. Now, we'll go through and check the dimensional analysis. You'll see that the grams of aluminum hydroxide canceled out, moles of aluminum hydroxide canceled out, moles of HCl canceled out, and then finally that's going to leave us with our grams of HCl. Okay, so let's punch all these numbers in here. I'm going to clear all that. 0.500 divided by 78.01. I'm going to hit enter. So we're here. We're going to multiply by 3. So times 3, enter. And then times 36.46. And that gives us 0.701. So 0.701 grams of HCl. All right. So there we go. That's how we calculated the mass of HCl that was produced. All right, we're going to do a very similar calculation for these next two. So calculate the number of grams of aluminum chloride and the number of grams of H2O. So we're going to calculate the two products. So I'm going to go ahead and write out the roadmap for each of these. So again, we're starting with our mass of aluminum hydroxide. All right, and we'll go to the moles of aluminum hydroxide, and then to the moles of aluminum chloride, AlCl3, and then finally to the mass of aluminum chloride. Okay. I'm going to go ahead and write out the other roadmap before I even pick up our calculator. So mass of aluminum hydroxide to the moles of aluminum hydroxide. And then we're going to H2O this time. So, all right. So our moles of H2O. And then our mass of H2O. All right, so now that we have the roadmap set up for each of these, we can solve the problem. All right, so at first this is going to seem really redundant, because we're doing exactly the same thing to start everything off here. So 0.500 grams of aluminum hydroxide. So mass to moles, we'll use the molar mass. Our molar mass of aluminum hydroxide is 78.01 grams of AlOH3 per mole of AlOH3. All right, and then moles to moles. Here we want to use the ratio in the balanced equation. And so 1 mole of aluminum chloride for every 1 mole of aluminum hydroxide. So 1 mole of aluminum chloride for every 1 mole of aluminum hydroxide. All right, then we want to convert to the mass of aluminum chloride. So we're going to need to get the molar mass of aluminum chloride. We want to get that molar mass of aluminum chloride. So aluminum was 26.98 plus chlorine is 35.45, so 3 times 35.45, and that gives us 133.33. So 133.33 grams of aluminum chloride per mole of aluminum chloride. Let's do the dimensional analysis real quick. So grams of aluminum hydroxide cancels out, moles of aluminum hydroxide cancels out, moles of aluminum chloride cancels out, and that gives us grams of aluminum chloride. So I'm going to clear all that, and we'll do 0.500 divided by 78.01. We'll multiply by 1. I'm not even going to enter that in. And now we're going to multiply by 133.33. 133.33. And that gives us 0.855. So 0.855 grams of aluminum chloride. Now, one thing that can happen is that you can get a little bit of rounding error. So sometimes the numbers don't add up. I think this one turns out okay, but I just caution you about that. All right, so let's do our last calculation with this one. So 0.500 grams of aluminum hydroxide, 78.01 grams of aluminum hydroxide per mole of aluminum hydroxide. Next, moles to moles ratio. We'll go back up to our equation. There's 3 moles of water for every 1 mole of aluminum hydroxide. So 3 moles of H2O for every 1 mole of aluminum hydroxide. All right, next we'll need the molar mass of water because we're going from moles to mass. We'll need the molar mass. Our molar mass here is 18.02 grams H2O per mole H2O. All right, we'll do the dimensional analysis again because there's nothing more fun than doing dimensional analysis. So our grams of aluminum hydroxide cancels out, our moles of aluminum hydroxide cancels out, and our moles of H2O cancels out. So 0.500 divided by 78.01. All right, we'll multiply that by 3. And we will multiply that by 18.02. And the number we get there, let's see, 0.346. So it's 0.346 grams of H2O. And we'll put that in a box. All right. So the last part here is kind of like what we did on the slides a few minutes ago. Show that the calculations in parts B and C are consistent with the law of conservation of mass. So 0.500 grams of aluminum hydroxide plus 0.701 grams, and that is for our reactants. I don't really need to put this in, but 0.701, and we get 1.201 grams, and that is our reactants. There we go. And now for our products, we'll do the same thing. 0.855 grams and 0.346 grams. 0.855 plus 0.346. And of course, we get 1.201 grams of products. Now, just as a note, when you're doing these, sometimes these numbers will be different in the last sig fig, and that's not because the law of conservation of mass is not true. It's just because there is rounding error whenever you do significant figures. It just happens. So like if you had one that was 1.201 and one that was 1.202 or 1.203, that would be okay. That usually indicates that that there was just a little bit of rounding error, no big deal. All right, well, let's go back to the in-class presentation. And we will look at, what do we got here? Oh, yes, we've got another stoichiometry example that I want to do. And this other stoichiometry example, all right. So how many grams of HNO3 are needed to dissolve 11.45 grams of copper? And when we say dissolve, really we mean react with. So how many grams of HNO3 are needed to react with 11.45 grams of copper? All right, well, here is, for this particular reaction, here is the balanced chemical equation. 3 moles of copper plus 8 moles of nitric acid will give us 3 moles of copper 2 nitrate and 2 moles of NO, nitrogen monoxide, and 4 moles of water. All right, so what we know is the mass of copper, and we want to get to the mass of nitric acid. So our mass of copper will convert from mass of copper to the moles of copper, from moles of copper to the moles of nitric acid, and from the moles of nitric acid to the mass of nitric acid. All the time when I am solving these kinds of problems, I will always write out a roadmap. Forgetting or choosing to take a shortcut and not write out the roadmap is a good way to come up with the wrong answer. All right, so our mass of copper, moles of copper. So the mass of copper that we had was 11.45. Mass to moles, we use the molar mass. So we'll need the molar mass of copper. And on the periodic table, I've got 63.546. We'll round that to 63.55. So 63.55 grams of copper per mole of copper. And you will see that the grams of copper cancel out. And then our mole to mole ratio is 8 moles of nitric acid for every 3 moles of copper. So we'll have an 8-to-3 ratio here. Then we will go from moles of nitric acid to the mass of nitric acid. And for moles to mass, we use the molar mass. And I calculated this earlier, and it came out to 63.02 grams of nitric acid per mole of nitric acid. One thing of note is you don't have to put the ones here. For whatever reason, I have a 1 there, but you don't have to put those ones there. All right, and we do dimensional analysis, and we get the mass of nitric acid out to 4 sig figs, just like our starting number. And now we will do number 63. So let's go over to our in-class assignment and look at number 63. So first thing, we need to come up with a balanced equation. It says calcium hydride reacts with water to form calcium hydroxide and hydrogen gas. Write a balanced chemical equation for the reaction. All right, so we'll do a balanced chemical equation. I'm going to do it above here to make sure I have plenty of room. So calcium hydride, well, calcium's +2, hydride is -1, so it'd be CaH2, solid. You don't necessarily have to put the states there, although Mastering Chemistry loves the states. All right, reacts with water. Well, we all know the formula of water is H2O. We'll put liquid. And it will form calcium hydroxide. Well, hydroxide is -1, calcium's +2, so we're going to have Ca parentheses OH, close parentheses 2. That one happens to be soluble. We'll talk about acids and bases here in the next chapter. And then hydrogen gas. And hydrogen gas is one of our diatomics, so H2 gas. So now we just need to look and see, is this balanced? And the answer is not quite. It's not quite balanced. Our biggest element here is calcium, so we'll start with calcium, 1 and 1. Our next biggest element is oxygen. We've got 2 oxygens here, only 1 there, so I'm going to put a 2 in front of that. And now we need to do hydrogen, so we'll need to add these up. So we have 1 times 2, there's 2 hydrogens there. 2 times 2, that's 4. 2 plus 4 is 6, so we have 6 on the reactant side. On the product side, we've already got 1 times 2 times 1, so we've got 2 accounted for. That means we need 4 more for this, so we're going to put a 2 in front of that hydrogen, and that will give us a balanced chemical equation. All right. So calcium hydride, there is our balanced equation. Now it says how many grams of calcium hydride are needed to form 8.500 grams of hydrogen. So the quantity that we know is our mass of hydrogen. And we're trying to get to the mass of calcium hydride. So we'll go from mass to the moles of hydrogen. All right, from the moles of hydrogen to the moles of calcium hydride. And then from the moles of calcium hydride to the mass of calcium hydride. All right, now that we've done that, get my other pen. I like to mix up the colors when I'm doing this. So we'll start with that mass. So 8 0.500 grams of hydrogen. Now we know that the molar mass of hydrogen is 2.02 because we've seen that multiple times. However, you'll notice here that we've got 4 significant figures, and hydrogen 2.02, that only has 2 sig figs. So we're going to get an extra sig fig here. So instead of using 1.01, we're going to use 1.008 as our atomic mass of hydrogen. So 1.008 times 2. And that gives us 2.16. So we'll use 2.16. 2.016. I said that wrong. So 2.016 grams of hydrogen per mole of hydrogen. Moles to moles, ratio. And so here we want to look at the ratio. We want moles of calcium hydride per mole of hydrogen. So 1 mole of calcium hydride up in the numerator, and then 2 moles of hydrogen down in the denominator. So 1 mole of calcium hydride per 2 moles of H2. And then finally, moles to mass. We want the molar mass. And get the calcium here. So 40.08 plus 2 times 1.01. And that gives us 42.10. We'll go out to the hundredths place. So 42.10 Okay. So now when we put that in there, here are, we'll do our dimensional analysis. Grams of hydrogen cancels out, moles of hydrogen cancels out, moles of calcium hydride cancels out, and that leaves us with our mass of calcium hydride. Let me get the calculator on the screen here. We'll punch all these numbers in. Exciting. 8.500 divided by 2.016, enter, divided by 2, enter, and then we'll multiply by 42.10. And you'll see we get 88.75. So 88.75 grams of calcium hydride. All right, so that is another stoichiometry problem. I'm going to say the only way to get good at stoichiometry problems is to work lots of stoichiometry problems. All right. Well, that is the end of this section. I believe the next page is the next section here. Yes, our next so I'm going to stop this here, and we'll do the next section in the next video.